Hello, my name is Jacob Brody, and I'm here with Jacob Tommy, Myungjun Lee, and Ethan Rossman, and we are here doing our IC Engines presentation. This is Group 1 in Section 3 of the Fall 2021 section of ME 4056. To begin, we're going to introduce the IC Engines problem. We're going to display some methods that we are going to implement to resolve and find a solution. We're going to present our results and some conclusions moving forward.
To introduce IC Engines Lab, we were going to go over backgrounds and objectives first. So this engine is developed by General Energy System. They developed a general generator based on a modular internal combustion engine, and they requested Birder to determine the system's parameters and control the system for the new system. So the objectives for this lab is to first identify IC engine properties, then develop IC engine work model, and lastly, to optimize the operation and timing of the IC engine. So this setup engine is connected to 48-volt regenerative motor, which can turn the engine or can be turned by the engine to store the energy. The encoder can collect the engine and motor's positions, and the force transducer can collect the engine and motor's torque. And this modular engine can be operated by either compressed air or propane fuel. However, in this lab, only air is used for safety purposes. The force transducers are calibrated for every runs of the lab. This is done by adding the weight on the transducer and taking them off back while measuring the voltage and the torque on the transducer. The voltage is used as an input and the torque is used as an output to calibrate it. In order to identify the IC engine, the team had to either measure or calculate search properties. These are also done on the force transducer and encoder. First, the team had to develop the IC engine work model. So on this model, the 3 rounds of the experiments are planned and characterized. That is to characterize the work terms in the IC engine work model. In the first round, the head is not attached and the air is not injected either. Therefore, the work done by the air and the discrepancy work are negligible. Flywheel angular velocity A and B are determined by the result of the experiment. The motor work can be calculated by taking numerical integration of the torque over the angular displacement. The frictional torque was calculated by taking the average of the torque in the steady state region. The flywheel moment of inertia can be calculated by adding motor work to frictional torque and angular displacement multiplied, then times 2, and then divide everything by flywheel's angular velocity squared. In the next round, to find the work done by the air, the head is now attached to the engine, but the air is still not injected. Without the injection, the work done by the air can be calculated by the summing of the work done in compression stroke and the power stroke. Equation 1 can be used to calculate the work done in adiabatic power stroke from engine piston position 1 to 2. Equation 2 can be used to calculate the work done in intake and exhaust stroke, which are 0, due to air is not injected to the engine. And this is done on the engine piston position 2 to 3 and 4 to 1. On equation 3, due to no air injection, the work done by the air in compression stroke is the negative of the power stroke. Equation 4, the discrepancy work can be calculated by subtracting the work done by the air by the experiment by the work done by the air by the model. The work done by the air by the experiment can be calculated by applying the numerical integration over the angular displacement. In order to optimize the operation and timing of the IC engine, the head is attached and the air is injected. The total work done by the engine can be calculated by applying the numerical integration of torque over angular displacement. 2 factors that affect on the work of the engine are acceleration and braking load. The acceleration will be determined by adjusting the timing of an air injection into the cylinder. The braking load is when the engine is trying to spin faster than the motor. To prevent this happens, the engine's RPM will be set as low as possible. The uncertainty of the work done by the motor is assumed to be the same as the uncertainty of the work done by the air. With that said, the uncertainty of the work done by the air is in conjunction with the discrepancy work. If the discrepancy work is not in the uncertainty bounds, the team can conclude that the model is not accurate enough.
We began by calibrating the force transducer by progressively loading and then unloading. We plotted the data points of the outputted voltage for the force transducer and applied a linear fit to derive a gain value to translate the values of voltage to usable torque. The first thing that was characterized was the frictional effects of the system. We removed the head, which eliminated the work due to air pressure on the piston. We assumed that the work due to the piston was negligible, leaving only work due to inertia of the system as well as friction. After running the engine up to a steady state RPM, we were able to calculate the total work and attributed that work to friction. We ran the system at 3 different speeds, low, medium, and high, gathering the work due to torque, and found that there was minimum differences between each of the 3 torque values. So, by analyzing the 3 different speeds and finding that there was a only small amount of difference between the different contributions of work due to friction, we were able to assume that the frictional effects could be modeled as Newtonian, which do not change based on the RPM of the engine. The average value of torque due to friction was 0.5657 Newton meters. Next, we were able to characterize the inertia of the system by looking back at the transient effects of the system. We were able to subtract the work due to friction during the transient phase, and then we found the inertia of the entire system and compared this to theoretically gathered values by measuring the geometry of the flywheel. The flywheel, in theory, came out to about 0.02 kilogram meters squared. The inertia of the entire system logically should be a little bit greater than this because it takes into account the inertia of rotating elements of the engine itself. We were gathering this data for 3 different speeds as well as without the flywheel in general. At low speed, we got a value of 0.01, which was less than the theoretically calculated value from the flywheel weight alone of 0.02, which seems to be incorrect, but the medium and high speeds were slightly larger than this, which do make a lot of sense. And without the flywheel, we were getting a value of 0.01, which is less than 0.02, the weight of the inertia of the flywheel itself, which also makes sense.
The work due to air can be found for each stroke by integrating under the torque versus angular position plot for the engine when the head is attached but no air is injected. Since the engine was zeroed at top dead center, where 0 degrees correlates to top dead center, the intake stroke is from 0 to pi, the compression stroke is from pi to 2 pi, the power stroke is from 2 pi to 3 pi, and the exhaust stroke is from 3 pi to 4 pi. The friction is also doing work against the motor, so the work due to friction found when running the engine earlier with the head off is subtracted out in these values. Here you can see the work due to air for the low speed, the medium speed, and the high speed. Altogether now, you can see the low, medium, and high speed values along with the theoretical values. Notice that for the theoretical values, the intake and exhaust strokes should be 0 joules. However, in the low, medium, and high speed, we had numbers that were significantly higher than 0. Overall, there was a large discrepancy between our values for work due to air.
Last but not least, I will be going over our conclusions for the past 2 weeks and the steps we will be taking next week to determine whether or not these conclusions are justified. To begin, the uncertainty was calculated for the work due to air for an entire cycle. This was calculated for both the model and the experimental calculations, and these uncertainties were calculated for the runs in which we had 4 flywheels on the engine. At the bottom, you can see graphical depictions of the uncertainties and the experimental and model values of the work due to air. The X's in red are the experimental values with their uncertainty bounds. It is evident that the blue X's are the work due to air of the model, and in all 3 cases, this value does not fall within the uncertainty bounds. So the assumption we would make is that there is some confounding factor that we are not able to calculate or account for in our model. Moving forward with week 3, we are going to begin with our sensor calibration per usual, collect the data for the work due to the engine, and then calculate our model. If the work due to the discrepancy in the model is greater than the uncertainty of the work, then we will reject the model and say that the discrepancy is too great. There is some other factor accounting for the discrepancy other than our experimental errors due to sensors, and if the discrepancy of work, the work due to discrepancy is lower than the uncertainty, the model cannot be rejected, and further investigation can make a more perfect model to determine our precision.